All right, let's fix this wireframe diagram, which is an absolute mess here. Let's repair this. What we have here is anatomically not possible, so I'm going to delete the link between 5 and 6. Click on 5 and 6 and delete that, and I'm going to instead link 5 to 7. So I'm going to link landmark 7 with landmark 5. The heck, just 5 with 7, right? Link landmarks. There we go. Now what I want to do is get rid of that link between 5 and 6. So let me find 5 and 6. Link 5 and 6. I want to delete that link. Okay. I want to delete the link between 7 and 10. I want to delete the link between 9 and 11. And I want to create a link between 9 and 6. Obviously not. Let's get rid of that. Okay, I want between 10 and 11. There we go, and 11. Okay, and now I want between 9 and 6. So I want to link landmark 9 with landmark 6. There we go. All right, there's a more reasonable illustration of what that thing looks like, so I'm going to accept. Okay, and now you can see the changes along PC2, and that makes a little bit more sense. And let's go back and look at PC1. Click OK, and there's the shape change between PC1. Notice there are as many principal components as there are landmarks. Okay, so that's always going to be the case. So if you have 14 landmarks, then you're going to have 14 principal components. What I want to do now is I want to, instead of looking at a principal components analysis, which is essentially just showing us where the variation in the data happens to be, instead what I want to do is a canonical variance analysis. And what a canonical variance analysis does is it answers the question, how do these groups differ? So it's going to show us exactly where these differences are. So I'm going to use my new data set, and I'm going to, my classifier is going to be species, and I am going to ask it for a permutation test, and I'm going to go ahead and execute it. And here is my canonical variance analysis. I can look at my CV scores, and the first thing you notice is that the groups are very much different. So let's go ahead and put in the confidence ellipses, and we're going to ask it to draw the ellipses and use species as a classifier, and we're going to use that the color of the associated with each species to match up with the ellipse. So there we go, and there you see the real difference, right? So you can see that black bears and grizzly bears are sort of on the same side, and it's the polar bears that are fundamentally different. The other interesting thing to notice here is that notice the trajectory of that ellipse. The main axis of that ellipse is going off in this direction, and for these two species over here, it's going in this direction. So that's where the allometry is going to be different on these guys, and that of course is why the polar bears are in an evolutionary cul-de-sac, so they are destined for extinction. And here again we can look at the wireframe diagram. So let's go back over here to the shape changes and look at the wireframe diagram. So yep, that's the one we want. And now you can see the difference between the polar bears on one side and then the grizzlies and black bears on the other side. Or we can look at the other canonical variant. So look at CV2, and there you have it. and there's the shape difference there. So there's something major going on here at the anterior part of the jaw. And of course, the angle of that mesenteric fossa is changing as well. So that, in a nutshell, is a very powerful thing that we can do in an effort to explore these shape differences between these species.